So Houdini 16.5 is out, and one of the features I'm really excited about was the incorporation of optical flow, which basically means we can now accomplish what I did in my previous tutorials, where we were driving simulations using motion vector data generated in Nuke. We don't need to use Nuke anymore. We can just do it all directly in Houdini. I just wanted to first give a special thanks to CG Wiki and Matt Estella, who runs it. First off, I mean, this is an amazing resource. If you don't already know about it, there's just a ton of information here. Amazing example files, setups, descriptions about everything. It's really fantastic. If you're trying to figure out how to do some crazy stuff in Houdini and you're a little bit stuck, I always come and check out this website to see if there's anything there. And I was a little bit stumped on figuring out how this new node worked, but Matt is on it, and he had an example file that really helped me get my initial setup rolling. And so I just wanted to give a shout out to him real quick and tell you guys about this website. You should definitely check it out. It's one of my favorites. So here we are. Let's get started. First thing we're going to need is a geometry node. We're going to hop inside, delete the file. Then we want a copnet. So if we type cop, it's cop2 network here. And within this, we get our compositing context. The compositing context, if we go over to this this composite view tab, this will show the images that are generated by our compositing context. So I'm going to drop down a file node, and we're going to read in my animation sequence here. And in the compositing view, if I middle mouse drag and scroll, you can see that I've got my animation sequence from one of my previous examples. At this point, I was thinking, okay, cool. Well, the optical flow node must be in the compositing operations, since, it seems to be sort of a compositing trick to be able to do optical flow. So I hit tab and started to write optical flow, and I couldn't find it in here or anything like that. It turns out that it actually occurs out here in SOPs. If I start typing optical, there's this node called volume optical flow. And I was like, volume optical flow. What is this volume about? Well, we can actually feed in volume slices to get it to do the trick. But before we get into that, I want to just hop back into the copnet and then put down a null so that we're staying organized here. I'm going to wire that in, call it out. And another thing I wanted to do is, to achieve the type of effect I'm after does not require that much detail, and I want it to compute a little bit faster. So I'm going to take the file size from its natural resolution down to 1/4. You can see it shrinks over here, but we still have the information there ready for analysis. I'm going to set the render and display flags to this null. Coming back up here in our copnet, our output source planes, it's outputting everything, which if we middle mouse click here is just, it looks like it's color, but we don't want to use a mesh. We actually want to use a volume slice because the volume optical flow takes in volumes. So what the node actually does is it takes a source image and a goal image and interpolates between the two using optical flow. Basically what it wants is it wants the current frame and the next frame that it's going to be looking at in order to determine what the motion vectors are. So to do that, I'm going to use a time shift. And so we can wire in the current frame on the left, and then we'll time shift by 1 frame on the right. So we'll just add a +1 over here. Since the time shift by default is just computing the current frame, we'll just add 1 frame to it and wire it in down here. I got to switch back to the scene view, and you can see that there's really not much to look at this point. Want to visualize this, we can actually add another volume slice down below. And set this to read the attribute CD. And I'm going to turn off visualize. And the method I'm going to choose is points. Now you can see it's created a grid of points. I'm actually going to change my display to be the background to be darker. just so it's a little bit easier to see. And I'm going to also turn off this display, this origin nomen. Okay. And let's get rid of the grid for now. So here you can see that it's pulling in the color information of the, optical flow motion vector data. But, I was initially trying to use this and it just wasn't working. And I kind of figured out what was going on. Now, when I middle mouse click on the volume optical flow node, I can see that it's creating 9 channels. And I was like, what is going on here? And apparently what it is that, when you're in this compositing network, you're actually outputting a red, green, and blue channel. And back up here, this volume optical flow is computing optical flow for the red, green, and blue channels. And we don't really want that. So the way I got around this was I was able to actually force this optical flow node to just compute based off of the luminance channel. So more or less a grayscale image. To do that, I went in here and dropped down a channel copy. And here I added a new plane. And I'm going to set it to alpha. So basically we're creating an alpha channel. And then for the input, I want to set color to be the input. So if we jump back to the compositing view over here, and then I click down in this lower corner and click the C. If I select alpha, whoops, here I set it to color. I want to actually set it to input 1 C. So now you can see this little image inside of here has gone black and white. If I go over here and select alpha, you can see that we get a grayscale image of our animation that we can use to analyze with the motion vectors. This seemed to work pretty good in this example. So if we go back up out to our geo and we middle mouse click on this, we can see that we get CR, CG, CB, and A. And down here, we get even more stuff. Now to mask this out and only really go after the alpha channel, we can blast away the other channels. So ton of blast. And we'll wire this in right above right below our copnet. So up here, back in the scene view, we go and select our blast. We can select our group to be the alpha group. So now it's actually deleting the alpha group. We don't want to delete the alpha group. We want to delete everything but the alpha group. So now we've got a black and white image out here in SOPs. And it's playing back at a pretty decent speed. That's cool. And then we time shift it. You can see it jumps forward by a frame. So we're using that to compute. We go to our optical flow node. We don't really see anything. Actually, you do see a little bit of something. It's kind of hard to see on my screen, but there's almost like it looks like a sort of a grayscale cloud being created in there. But then we hop down to the volume slice, and we're starting to get what we would expect to see. It's still pretty dark, but you can see that it's creating that red, green, and yellow type of a vector image that we were after when we were creating our motion vectors in Nuke. So cool. Now, let's go back to the volume optical flow node for just a second to go over what some of this stuff is. I was at first very confused. What are pyramid levels and pyramid scales and all this stuff? And I ended up going on some tangent to go read about optical flow, and I'll tell you that it is quite high level stuff. So yeah, I spent some time looking into what all of this stuff means so I could get the most out of my optical flow vectors being generated in Houdini. And it's really cool because this actually gives you a decent amount of control over how the optical flow vectors are computed. So a lot of the clues that I got, I went to the Houdini nodes, geometry nodes, and read through this volume optical flow geometry node. And essentially what these are parameters used by the optical flow algorithm to determine how much detail they're going to go into analyzing. And the optical flow algorithm actually uses layers, which they call pyramid levels, to compute changes in pixel data on various levels of detail. So if we look at Photoshop here, this is sort of an image of our pyramid. And so at the bottom, we have the full resolution image, and then we go up here and we have a slightly lower resolution image, and up here we have an even lower resolution image. So there's 3 layers. these images. And then what it does is it goes and analyzes each image in succession. It might go the other way around, I'm not sure. But and then it combines all of that data into, the final vector flow field that makes up our red, green, and yellow images. For me, I turned on the Gaussian filter and cranked up my pyramid levels and left everything else at default, and I felt that that did a pretty good job for what I was after. Feel free to explore these and play around. I'm by no means an optical flow expert. I don't quite understand how it all works, but I'm really excited about the results that it produces, and I think it's something that everyone should be able to have fun with. So now that we've got our motion vector being generated directly from Houdini, a lot of what we're going to do is similar to the previous example, but I'm just going to go through it for the sake of completeness, because why not? So let's drop down an attribute wrangle. And we're going to use this attribute wrangle to set our velocity. Because we have these colors, but they're not actually mapped to our velocity. We can see that we've got 2-point attributes, we got our color and our position. If I go over to our geometry spreadsheet and look at the color, you can see it's red and green values. And then the blue value is 0 because there's absolutely no calculation of Z motion or Z velocity in a 2D image. So we've got our X and Y velocities here that are being stored in color attribute. So what we can do is we can just remap them to velocity. And it's simple enough. We're just going to say at V equals at CD. Those at symbols being attributes. CD is our common color attribute, and we have just mapped it onto the velocity. So let's turn on the velocity vectors. You can see that they've kind of showed up a little bit here. They're kind of hard to see. They're very small, but I'm going to actually multiply this CD vector by a parameter that we define so that we can, enlarge the incoming velocities to make them more, to scale them to the effect that we want. So I'm going to add a times channel float, open quotes, and we'll call it multiplier. And we'll hit this little button down here to create it. And you can see that they went away. I'm going to crank this up to, let's crank it up to 100. And you can really see our motion vectors starting to appear as actual vectors. Yeah, you can see that when we got some large motion like this, they're kind of flowing around and fun. Cool, so we're here, but we don't really have the colors of the original image that we want that we're going to need for our emitter. So the other thing we're going to have to do is we're going to have to split the stream up top here where we were just blasting away our color for our alpha channel. We're going to want to do the same, but we're going to want to do the opposite. We're going to want to do a similar thing, but instead of blasting everything but alpha, we're going to blast alpha and be left with color. And we're also going to feed that into another volume slice, similar to this one. And here we're left with pixels that are in the color that we're looking for. If we hit the display, I'm going to just change the background color to light real quick to see that we've got all those black pixels in there as well, which we're going to get rid of in a second. So we've got the volume slice and we've got our velocities over here. And we just need to copy now the velocities back onto our colored pixels that we want. So we're going to add an attribute copy. And wire this guy in here and this guy in here. I'm going to hit Shift S to make my lines this nice curved shape. And here it's by default, it's copying the color back over to these points. We don't really want that. We actually want it to copy velocity instead. So I'm going to select velocity from the dropdown and just delete CD. And there we are. So we've got our colors, our velocity vectors. Sweet. I'm going to turn off these trails for now. Then this next node, we're going to need another wrangle. I'm just going to pipe the velocity into a local variable called vel. And we're going to set that equal to the attribute of velocity. And here we can use this to sort of remap our velocity values. Over in our geometry spreadsheet, So here we have our X and Y velocity. I just want to add a little Z velocity to push it back in the scene behind the currently emitted particles, just so that we can have sort of the particles that are being created kind of prioritized to the front of the image. So let's go down here and we will say float VZ, and we'll set that equal to the absolute value of vel.x plus vel.y divided by 4, and then we'll map those back into V. Set V equal to vel.x, vel.y, and VZ from up here, and close that off. So up here, our velocity vectors look like this. Down here, they've been remapped slightly to be sticking behind the image. But actually, these are velocity trails, so I want to actually put a negative sign here in front of this absolute value so that they are actually being pushed. If this is a trail, it's actually being pushed backwards into the plane. Cool. So I'm going to just do a couple other things. So I'm going to add a multiplier. We'll go up to the top here and say float mult equals CHF multiplier, just like we did on the other one. And we'll hit this button here. It creates a multiplier, and we'll attach that down here by saying mult, and multiply this whole thing by that. So here we can adjust the magnitude of our velocity down here. Other things, let's get rid of the black pixels. To do that, I'm going to set a brightness threshold, and that's going to be similar. Up here, we'll make a float variable. We'll call this thresh equals CHF threshold. And down here, what we'll do is we'll create a vector to pull out the luminance of our image. So vector HSV is equal to RGB2 HSV. And the vector we want to convert to HSV is CD, the color attribute. And then we'll use an if statement. We'll say, if the third component of the HSV vector, HSV.z, is less than whatever our threshold was that we set, do the following. I want you to remove the point from the first input, and the point number is going to be at PT_num, the currently evaluated point. And we need to then hit this button once more to, it's upset at us because we haven't created our actual threshold slider yet. So we'll click that. And it's also upset because I used a square bracket here, so we'll make that a curly one. Awesome. So now you can see that. Let's turn off these. Let's turn off the velocity trails. That when I take this threshold up just a slight amount, it deletes all those black pixels, and we can take that up as far as we want. So we'll set it. We'll just leave it set about there. That should be good. Hit stop. Okay, so now it's time to create the particle fluids. So up from our shelf up here, we've got our particle fluids tab, emit particle fluids. In order to get this to go, if I go up here and I select our geometry and I click emit particle fluid, select I don't have a fluid object to emit into. Just hit enter. And it says no surface found. It's actually looking for a surface, not a bunch of particles. So I'm going to trick it real quick. I'm going to jump into our geometry. I'm going to change these. I'm going to select both of these volume slices, and I'm going to change these to mesh instead. So then if I make sure attribute wrangle has a display flag on it, hop up again, select our geometry, and then say emit particle fluid, it should be fine. And press enter. And there it's created it. It's created our surface volume and all that stuff. So let's fix this now. We want this to be points. So I'm going to change this back to points. And then under our create fluid surface volume, I'm going to say stamp points. instead. So now we should be all good. So let's, I'm going to hit the U key and I'm going to drop into the auto dop network and hit the L key to lay this all out. And let's see what we're working with here. I'm going to go up here in this little menu and I'm going to say hide other objects and see what we got. Cool. It looks like a fluid sim that is behaving, it's emitting from all the right places. It looks like it's inheriting some velocity. I mean, that was, this big splash up front. That's cool. But our container is really huge and we don't have the particle color on the sim yet. So I'm going to switch back to a dark background at this point. We're going to say dark. And what I'm going to do over here is I'm going to go to our CopNet, this image, and I'm going to create a bounds that we can reference here so that we can so that we know that whatever size this is, it's going to procedurally update the size of the flip sim. So I'm going to take a bound. And this basically makes a bounding box, which is wafer thin, around our compositing network. And I'm going to just set the padding to be about, 0.2 in every direction. That way you kind of have a little bit of a, little leeway there. And then I'm going to I'm going to put a null here for bounds, just so it's easy to reference from our auto dop network. And yeah, so let's hop up here and go into the auto dop network. And on our flip solver, I'm going to go to the volume motion tab, and where we got our box size, I'm going to set our X to the size of our bounding box. So I'm going to say bbox. Using the bbox function, I'm going to refer to up one level, up two levels, then into Go1, and then to our bounds. And I want, here it gives me a bunch of options. I want the dx size. So d_x size. And then it snaps the width of the flip tank to the x size of the bounding object. Let's do it again for y. I'm just going to go here. I'm going to select all and copy, and then go into the y field and paste it and change dx size to dy size. And there we go. And then in terms of the thickness, I don't want this set to the thickness of our bounding box. I'm just going to set it to something like 3. Should be good for us. I'm not sure why the box center got moved out to 4, but I want that to be centered around 0 as well. So there, we've got our sim nice and contained in a nice small confined area. Another thing I want to do is I want to go to the flip object and I want to turn on closed boundaries for some of the boundaries. And the boundaries that I want to close are basically all of them except for the positive Z boundaries, so that it can splash around inside this box but then flow out the front. So I'm just going to turn off closed boundaries on the plus Z. And great, let's quick hop up to into our geo network here, and we've got our create fluid surface volume. The other thing I want to do here is just an attribute transfer to get our color back. And we'll go like that. You can see it's grabbed color. I don't really want to grab any of the primitive stuff, so I'm just going to say color just to specify what we're after here. And then here what I'm going to do is I'm going to use, a Houdini 16 feature, which is the bookmarks feature. And I'm just going to hit inside of this view because I know I'm going to be going back and forth between here and dops a lot. I'm going to hit Control-1 to set a quick mark 1 here. Then I'm going to hop over to dops, and then I'm going to hit Control-2. So now if I go on my, on the keyboard along the top and hit 1, 2, 1, 2, I can just hop back and forth between these two networks really fast. So let's rewind our simulation and see what we got. It's still the color, it still isn't the right color, and there's a thing that I forgot to turn off. If I go into the flip fluid object, and I go to particles. The visualization type is speed. I'm going to set that to none. And that should make it so that everything is inheriting the right color. And let's play that back a little bit. Cool. I'm going to set the real-time flag on down here. And cool, there we are. Then it's just a matter of, tweaking your sim and all that stuff. Reduce the particle separation and let it play through. So maybe at this point, if you're not getting the right motion, you can go back and retweak your simulation, retweak your optical flow node to, maybe be more detailed or less detailed, depending on what the requirements are of your sim. One thing I am noticing here is that, a lot of these particles are like, they're living quite long and piling up down here at the bottom, and which is fine, but I kind of want I don't want them to steal the show away from the main content that's occurring up here. So what I'm going to do is I'm going to add I just want to give the particles a little bit of an age. So let's go back. I hit 1 to go back to my other context here, to the geometry context, and I'm going to go to my attribute wrangle down here. I'm going to create an integer birth frame equals at frame. What this basically says is, at whatever frame we're in, when you analyze all these particles, if we're on frame 2, all these particles get the birth frame of at frame. So if I hop over to the geometry spreadsheet, I can see we're on frame 12. All these particles have a birth frame of 12. Now, the other particles from the previous frames are, playing around in DOP still. They have their own birth frames of 11 and 10 and 9 and all that stuff. So we've set a birth frame here so that we can, determine its age out in SOPs. And when we export, if I go up and down here in our particle fluid, where it imports our information from the DOP network, I'm just going to select this. This is more or less our DOP network right here. If we look at the attributes, it doesn't have birth frame along with it right now because we haven't simmed it. So I'm going to quick mark this number 3 and go back to 2, and we're going to run it for a little bit. Cool. So if I hop over to 3, middle mouse click, and it's not getting the birth frame. The reason is I didn't transfer it back to the emitter. So let's hop over to 1. And in this attribute transfer, we're transferring color back to it, but I also want to transfer birth frame back to it. So I just click that and it adds it to the list. So that's cool. Hop back to 0. We'll hit 2, go into our auto DOP network, and we'll start simming that for a little bit. And then we'll hit 3 to go into our particle fluid. The middle mouse click on this, you can see that birth frame's coming through. If we look at the geometry spreadsheet, we got some particles born on frame 9, some on 8, 6, 3, 2, 1. Awesome. So let's just add a little bit of control to that. So I'm going to create a wrangle. I want to give the particles a lifespan and tell them like how long they can live and have them randomly die, sort of like trap code allows you to do. And so we'll just we'll make that happen over here in Vex. So let's compute the age. I know the birth frame of the age and I know the current frame, so I can create a float attribute age and say that the age of the particle is equal to the current frame that we're on minus the birth frame. So you can see that a particle born on frame 12 has an age of 0, and a particle born on frame 0 has an age of 12, and so forth. So let's set a lifespan. I'm going to go up here and drop down a float called lifespan, and we're going to set it equal to a slider. CHF, lifespan, close, and let's create this. Lifespan slider, it's not doing anything yet, but down here what we can do is we can say if our age is greater than our lifespan, then we want to remove point. Remove point from the 0 input, and the current point is the one we want to remove. Now you can see the lifespan is in frames, so we actually need to crank this up higher. You know, if we start going by integer values, you can see that it's actually deleting some of our particles away. That's great. Let's give them a lifespan of 2 seconds. So that would be 48 frames. And let's play back. Cool. Now, one thing I was noticing, I'm not really seeing it here, but one thing I want to make sure is that, you know, we don't have this sudden jump where a bunch of particles suddenly delete. Like between frame 49 and 50, a lot of those leftover blue particles from the initial blue triangle here, you can see them kind of click off. So let's add a little bit of randomness to the lifespan. To do that, I'm going to add another variable here called float life rand, and that's going to be equal to a channel float called lifespan randomness. And there we go. Make another slider for it here. And then down in our age function, we'll add in a rand of ptnum times some seed, which we'll call 969, multiply by 969. It could be any number. And then we'll multiply that times life rand. So basically what this is going to give us is it's gonna say the age of our particle is equal to the current frame plus some random number between 0 and whatever life rand is minus the birth frame. So if we do something like set the lifespan randomness to 48, some particles are going to begin to die immediately, and then it'll be very smooth transition. But you can see that's almost a little bit too much, because over here we've got just a pile of particles that are very separated from one another. So I'll just change the lifespan randomness down to something like 24 just to keep it a little bit more dense. I mean, you can play around with this. This is all just sort of personal preference at this point. Cool. And that about does it. I hope you guys have fun and find up some cool uses for how to use optical flow in Houdini, and I'd love to see all sorts of kinds of examples you guys come up with, and this is really fun to figure out, and I hope you guys just have an awesome day.